Well, good day and welcome to today's IMarEST webinar brought to you by the Naval Engineering Special Interest Group. I'm Matt Bolton. After a long career in the Royal Navy, I'm now Director and Principal Consultant with MTWB Consultancy Limited. I'm also having the privilege of hosting the webinar today, and I'm the Chair of the Naval Engineering CEG. I'm very pleased to say that the membership of our CEG continues to grow and now stands at well over 600 people from 44 different countries, which, to put it into perspective, is 3.5% of the total IMarEST membership and is a testament to the truly global interest in our domain. Last month, we held our first webinar outside the UK, with Mr. Patil from Larsen & Toubro providing a fascinating insight into the Indian naval sector, delivered from India and hosted by Commodore Rakesh Rana. I very much hope we can build on this and invite all of our members from around the world to offer their ideas for future webinars that can be hosted from their own location. Coming up, we're in the final stages of preparation for a live panel discussion on AI and automation. And sticking with the theme of AI, today we're looking at a particular application of this technology to improve the reliability and availability of machinery. Today's event, entitled Engine Reliability and the Role of Artificial Intelligence, is brought to us by Karl Hinks of Wartsila. Karl has over 40 years of marine engineering experience, including 20 years in the Royal Navy, before his commercial career took him to Solent University, where he headed the Maritime Training Consultancy Group, followed by 5 years at L3 Communications with their Maritime Training and Simulation Division. In 2012, Karl joined Wartsila Ship Power, working with ship owners and naval architects to build new projects. In recent years, he's played a key role in the machinery design for several diesel-electric hybrid vessels in the UK, including 2 hybrid ferries. Part of the design employs AI technology to help ship owners and operators minimize unscheduled downtime and get the maximum life from their machinery. Before I hand over to Karl, may I remind you that we'll be having a discussion at the end of the presentation, and you can post your questions in Slido using the hashtag reliability. So just go to slido.com, enter hashtag reliability and post your questions in there. So without further ado, I'd like to hand over to Karl.
Thanks, Matt. Okay, so hopefully you'll be able to see my screen. Confirm, Matt? Yeah, nodding. Thanks for that. Thanks also for the introduction, and thanks for the invitation to give the presentation to a wide audience. I hope you find it interesting and thought-provoking. I look forward to any questions that you may have a little bit later on. Just to give you a little bit of background, Matt's already given a pretty broad brush background, but just to highlight the number of vessels that I've served in a 20-year career, really, in addition to what Matt said, you know, ranging from LPDs some years ago in '83, and leaving. My last job was a neo of HMS Exeter. Since then, I've had a commercial career, both with Solent University and L3 Communications, who the Maritime Simulation Division was to do with the human element and performance, and that the company was based out of Salt Lake City, and then joining Wartsila, as it was Ship Power then, it's Marine Power today, and I accepted the job in 2011, started in early 2012. And since then, I've been working with naval architects and consultant marine engineers in the design of a host of new build vessels, not just commercial vessels, but also warships and support ships as well. So without further ado, We're going to look at artificial intelligence and its role in helping to avoid unplanned breakdown and increase reliability and safety and efficiency. And then we'll move on to a slightly shorter section, which will cover, again, the use of data in dynamic maintenance. In other words, not sticking strictly to planned maintenance routines, but using the data that we've collected, which we've used from the artificial intelligence system and data collection unit, and using that to increase or to identify, maintenance tasks based on condition. A little caveat from myself, although this covers essentially a Wartsila product, which is the expert insight system. If I give you an opinion, it will be purely my own and based on my own experience. So yeah, hopefully it will come across from kind of a wide range of experience over a 40-year marine engineering career. So I included this slide because it tells a picture, it tells a story of how military vessels are now being designed and constructed, and that is mainly as a diesel electric configuration, and that the increasing amount of electrical power that's needed for naval platforms is, I don't see that as reducing any, mainly because of other systems, like weapons, rail guns and things like this, and electronic warfare will also put a burden on the machinery within the vessel. And it's, it's the case that these vessels today are strictly, power stations, floating power stations, and to be able to float, move or fight in any particular order is hugely dependent on the reliability of the core equipment in the marine engineering department. So typically the watchkeepers down in the either ship control center or machinery control room these days, they have charge of a considerably expensive and complex machinery system these days. They have a lot of data to look at. Millions of signals are trending in the background in the IPMS system. Dozens of pages of schematics with hundreds of different systems in. And the watchkeeper, it typically will be it will be brought to the attention of the watchkeeper when a particular threshold is met with a particular piece of equipment. And there isn't usually that much time before going from alarm or into alarm or even shutting down completely. And those of you who've spent lots of time at sea, it starts the adrenaline running when you hear machinery breakdown, generator failure, as to what you're going to find when you get down there. But it's never more critical these days than with diesel electric vessels and very large diesel gensets. But the watchkeepers are under quite a lot of pressure to make the right judgment call, and not acting quickly enough, or if the equipment doesn't shut down and doesn't cause a trip, then consequently the damage could put the equipment out of action for long periods of time. So up until now, we've got machinery parameters, if you like, hundreds, if not thousands of different signals from the engine. And you have, basically an envelope of which the equipment will operate. And it will come into alarm when it exceeds a particular threshold. And it may well shut itself down, or it may well come back into limits, depending on a lot of different variables, including things like ambient temperature, air inlet pressure, differences in the fuel, calorific values and things like this. So this is very much a kind of digital system. It's either in or out of parameters. The problem with that is that you don't get a very long time before you have to react, or the system has to react before taking the equipment out of service. And clearly you don't want to do that without bringing a second or a replacement generator onto the board. So it's a bit like a human being. There's no way that he's going to be sitting in the machinery control room or ship control center looking for this information. And even if they're looking at the trending data, the differences in the signal parameters can be so small that a human would have difficulty identifying the anomalies, but B would probably, it's very subjective, it's very individually based judgment on what they consider, what the operator considers to be acceptable or not acceptable in terms of a parameter. But essentially a computer can do this all day long, running in the background, trawling through the data and trying to learn what would be typically normal behavior and what would be abnormal behavior. And that's really where this presentation starts, is in the role of artificial intelligence and machine learning. And every engine has its own particular footprint, if you like. It's not as simple as putting a threshold value, because due to a number of different factors, not least engine tolerances, in the manufacture, but also equipment material differences, every engine will be just slightly unique. So being able to identify early, or certainly learn the behavior and then identify anomalies, differences in behavior of a specific asset is hugely beneficial. So for that, we use two layers of what we call two layers of detection, the artificial intelligence being one, and the traditional rule-based mathematical models being the other. And the system will look at both of those avenues and determine whether or not it's acceptable behavior, what it's expecting to see or it's not. And at that point, the system will be analysed by an engine expert who has access to a lot of other experts as well. And in a little while, you'll see just how critical that can be, because artificial intelligence on its own is just a tool. What you really need is the kind of interrogation, the analysis and the experience to be able to make a judgment based on what you see. And clearly, we don't want to be alerting the vessel every 5 minutes of a small change in a parameter if it really doesn't matter. On the other hand, we absolutely want to be alerting the user to issues that are going to ultimately cause either wide-scale damage or impact on the safety of the operators. So I've already mentioned that the fact that every engine is unique, and what you see in front of you, a bit like a spirograph drawing, this shows you the interdependencies of all the engine signals. So in isolation, you can't just take one signal and monitor that and say, that's how that's how it works, because the engine is quite a complex beast. But artificial intelligence will take that information, it knows what these interdependencies are, and it works out whether or not it thinks there is a potential anomaly before flagging it up to a human, basically. And if left unchecked, clearly they can result in a breakdown. What we're trying to avoid is a breakdown at the most inconvenient time. So, however good your people are and however well trained they are, they're never going to be as knowledgeable as the experts, the OEMs. But equally, navies don't want people, rocking up every 5 minutes and getting involved with breakdowns. It's just not cost efficient. If you can automate that and you can do stuff remotely, then that makes an awful lot of sense. So here's the system kind of in its entirety in terms of the engine and the sample rate from the engine of the signals, which is about 1 a second. And if you were to compare that to a traditional CBM system of yesterday, then they would look at a whole load of data, not necessarily at that sort of frequency level, but they'll then look at monthly trends or averages, which is not very accurate. The system itself has firewalls, a data collection unit, and the information is shipped ashore into the cloud and off to the engine experts. They will only be alerted to things that are considered to be critical and out of parameters. But they've got access to other technical folks within the organization, and to give the equipment full 24/7 coverage. Although you only see Europe and the Middle East on the screen in the right-hand corner, there are essentially 3 data performance centers across the globe, of which the customer can know that they've got 24-hour coverage. So I know what some of you may be thinking, that these are military vessels and it won't necessarily work in a military environment. And yeah, you're not commercial vessels, and knowing where you are and what you're up to, you don't want others knowing that. But if you think you're any different to the commercial operators, I don't think that's necessarily true, because they have the same concerns and the same problems. The enemy may be different, but the task is the same. So whether you're an LNG carrier or whether you're a cruise ship, having the artificial intelligence look at the data and alerting you to potential problems is hugely beneficial. Especially if you took a cruise ship, for instance, the amount of equipment and systems on board there, and the cargo is very vocal, and it's all very much in the public domain if things don't go quite to plan. It's just that you do business in slightly different ways. So here's an example of a real case. This was a vessel, a dual fuel engine shuttle tanker. It was en route to pick up its cargo. It had the expert insight system fitted. And the screen now gives an indication of how the system communicates with the vessel. This may well be slightly different in a warship, given kind of encryption needed or the timing of the communications. But essentially, what happened here is that, given the data that had been transmitted to the performance center ashore, the operator then said, well, we've spotted something that is an anomaly. Please go and check the obvious. This is when we found that we saw a difference. And in the meantime, I'll go and talk to the turbocharger specialist. So sometime later, the crew had said, thanks for that. We'll fit the manometer. And yes, we agree that there is a very small variation in lube oil pressure to the compressor bearing of the turbocharger. Now, ordinarily, a lot of people might just say, well, it's a small increase, not a problem. If it was a decrease, that might give them case for more concern, perhaps. So at a certain point in time, the turbocharger specialist gave his feedback. the operator was contacted and said, yeah, we really need to get the engine shut down and investigate further. So this is what the expert knows as well, which is, I was surprised actually when I started researching and looking into this, just how powerful and how kind of dangerous turbochargers could be. And the sort of forces that are involved and the velocities involved are incredible. So for a 10 megawatt turbine power, which I grant you is the upper part of the scale, you know, you're looking at 97 tons per blade and 3,200 tons for the whole unit, which is essentially the same kinetic energy in the shaft as a large truck traveling at 95 kilometers an hour, which surprised me. And that's not to mention the temperatures involved. So if the turbocharger lets go, then you can imagine what happens to the shards that come off the turbocharger as well, should it catastrophically fail. So here's the other end of the scale. This is off a 800 kilowatt turbine. So that being around about the size of the output of 7 medium cars, family cars. Same sort of thing, kinetic energy is significant. So it's still the size of a medium-sized car passing at 90 kilometers an hour, which is still pretty scary. I'm talking to one large ferry owner probably a week ago about this exact thing, who, and I quote, "We've had several let go, and you don't want to be in the engine room when it happens." So this sort of thing can and does save lives. So in terms of turbocharger behavior, this is just a slide to show you the sort of damage that can occur progressively over the life of a turbocharger, depending on how it's operated, the environmental conditions, exhaust gas temperatures, the number of cycles and the load. So creep is something which a lot of navies will be familiar with gas turbines in particular. Won't come as any surprise, but also cyclic fatigue, which obviously imparts a lot of stresses in certain key areas. So these are the things that can become problematic. So I'm pretty confident in saying that in this particular case, that having the artificial intelligence absolutely prevented something like this happening. And this is an expensive piece of the engine. You know, it could cost upwards of 300,000 euros, or maybe $500,000, depending on the size of the engine. It is significant money. But not only that, if the parts of the turbo decide to deposit themselves in the charge air cooler, then that's even more work. So it's a significant catch, if you like, from preventing a failure. So here's another example which naval vessels and operators will be very familiar with. It's quite common, in fact, certainly from my time at sea, that we saw fuel dilution of lube oils. And typically we used to analyze the lube oil sample locally on board, but we also used to send it off remotely to somewhere like Cobham. And quite often it would come back and saying, you've got a percentage dilution of lube oil. Nobody got excited, but it did mean that it meant that we were going to have to change the lube oil. I think what isn't kind of readily apparent is, well, what happens if it continues? We're already seeing high main bearing temperatures within this engine. So if it goes unnoticed, or you don't do the routines that you should be doing, then this can end up with big end bearing or main bearing failures. And lube oil is expensive, and all fluids are quite critical to endurance of a warship. So it's quite awkward to be ordering tankers or large volumes of lube oil when you're deployed. So at this point, we've looked at artificial intelligence and how it can be used to prevent the unexpected. What I'd like to do now is to move on to cover a bit about data-driven maintenance. This is quite a short section, but it's still quite important because the data that you're collecting is very important to be able to, know whether or not intervention is necessary. And while, doing maintenance to maintain the maximum level of availability and readiness in the vessel is important, perhaps less important, certainly in past years, is looking at things like engine efficiency. And if engine efficiency drops off, then it may not be a big issue, but it will, or it may, impact on endurance and the frequency of replenishing, because you're clearly burning more fuel than you need to. And that may be, it may be a small amount, but it may be the case of a day's transit. It could be important. So the other thing is maximizing component lifetime. So in the commercial world, that would be value for money, and trying to get the engine or the asset to the sort of values that are predicted by the engine OEM. And if you don't need to intervene, or you don't have the correct intervention or the correct skills, qualifications and experience, then it's less, it's more critical, shall I say, to have that data to know whether or not you are going to do the work or you're not going to do the work. And if you've got the information and you've got the right people and you do the work, then there's less likelihood of emergent work. Variation always come out of that. Some would say prevention is better than cure. I think that was a Dutch philosopher, I don't remember his name. And some people would say if it's working well, leave it well alone. Yep, the caveat being that provided you have the data to support that, and you know how to interpret it. And I recommend fluid analysis at the same time. So it can be economic to employ data-driven maintenance and only intervening when the data and the evidence supports it. And when I put data-driven maintenance reducing risk, I put this slide up. This is the a typical conclusion of a P&I Club report on main engine damage. So you can see the sort of things that they think are contributing quite significantly to the cost of machinery damage to the pool of people within the P&I Club, or which are being claimed on machinery insurance. And one of those being that not having the experts in attendance at major overhauls, or insufficient training and experience, that can cause issues later on for sure. So yeah, one thing I don't want you to forget, which gets taken for granted certainly by others in the vessel, the warfare department, that machinery spaces are inherently hazardous, probably just as much or if not more so than weapons spaces in terms of hydraulics and electrical machinery. Clearly, we've got a lot of systems with fluids and gases, high pressures and temperatures, hot surfaces, rotating machinery, and free surface occasionally in the bilge. And any identification of potential defects will help prevent catastrophic and costly failures, injury to personnel, and extended times to repair. Not least to say that if you're operating in a task group, which most times you will be, then it could cause kind of political embarrassment if you can't fulfill the role in which you're employed within the task group. So I put this in to say who can relate to this, and it's basically saying that after a period of planned maintenance, HMS X sailed from Portsmouth, operational sea training and subsequent deployment, 50 minutes after passing the nav tower, increasing speed to 15-20 knots, then high bearing temperatures, closely followed by machinery breakdown, standing sea fire party close up, and ultimately, God forbid, fire. So that was quite a common occurrence, I would say, during my time. Not necessarily the fire, but certainly coming alongside to do maintenance, and then after leaving base port, not long after, the equipment that had been maintained was typically the ones that flagged up straight away to be problematic. Could well be, down to intervention, maybe not, non-subject matter experts. But the fact is that, it was decided to open the gearbox up or open the engine up because it said so in the planned maintenance. The problem was that nobody could tell you either way, good or bad, that was a good or a bad thing to do. So the principle of data-driven maintenance is obviously a black box data collection unit, looking at all the signals as we've shown previously with the artificial intelligence. But then from that data, you can decide whether or not that you may have to bring the maintenance forward to match up with a deployment schedule, or kind of small inspections of maybe one cylinder coupled with the data from the data collection unit, followed by OEM advice. You may be able to push whatever maintenance it is either later into the same window prior to deploying or further. Excuse me. So yeah, it's having that information and being able to make decisions based upon it. So in conclusion, we're probably a little bit ahead of time, but I'm sure we'll have plenty of time for questions. In conclusion, a warship is a very power-hungry beast, and it's dependent on high-quality, reliable source of electrical power. As I've said, the engine is unique in many ways because of machinery tolerances and also the where it's fitted in the ship. So you might have a long inlet or a long exhaust trunk, or where it's what the ambient conditions where it's sucking from. It's one thing just taking the data and trending it, but by and large, and naval circles are not alone when I say this, is that the data tends to go in a drawer and then not used or acted upon. So for sure, engineering judgment is made easier with data. And I would say artificial intelligence is a step change and essential for a complex naval platforms in their daily life. It's a system which can learn, and it spots anomalies very early. It does things that the human can't do, and it provides a level of control and over the reliability and performance of the engine. And modern technology means that this is it's achievable today safely and securely, cyber securely. But it's AI and data are nothing without having the expertise and the understanding to be able to provide the support and the advice to the user. And as I said, it certainly would help maintain OC, prevent the unexpected, absolutely improve safety in the engine room, and potentially extend time between overhauls and facilitate dynamic maintenance. And the last thing really is the fact that data collection and artificial intelligence, although we've covered it here in a diesel engine, that it is, obviously usable in other equipment. the question is then the expert for that equipment to be able to provide the feedback. So, for instance, we're using it on exhaust after treatment units, and it will be used on 2-stroke engines as well as 4-stroke engines. And that really is me finished. I hope that was enjoyable and beneficial.
Great, thank you very much indeed, Karl. That's it. Stop the screen share. That's great. We can get into the discussion. So thank you very much for your presentation. Before we get into the discussion, if I can just remind our audience, it's very easy to post a question. If you just go to slido.com, that's slido.com, and then enter the hashtag reliability, you'll be able to access our question Q&A session and post your question in there. So we've got a few come in, but just before we sort of get into the AI discussion, one of the things that's always troubled me with respect to the provision of remote-based support has been the fact that naval vessels can't continuously be connected to shore and may go for many, many days without a data link available for machinery performance information to be sent to shore. So how does this approach cope with that unpredictability in information flow?
Yeah, thanks for the question, Matt. It's not necessary to transmit the data in real time. The periodic transmission of that data can be as and when the ship can transmit it, because they're looking at the data so early on that the likelihood of you having an event in the time that it's taking you to transfer that data and to get the expert to look at it, you've still probably got time before something catastrophic is likely to happen. So one possibility, I guess, would be, depending on where geographically the vessel is, but I think every day the ship releases a log wreck at midnight. So I'm not sure on the kind of the mode of transmission of that today. Certainly in years gone by, it would have been obviously through either HF or medium wave frequency or whatever it was, I don't know. But today's modern, satcoms, it's possible to get, I would say, get that equipment, get that data off the ship. Equally, there would be nothing wrong with waiting until the next port visit to download a week's worth of data. It's really, whichever way you do it, it's going to be a large improvement on what they've got today, which it's kind of old technology. Well, old processes, I would guess, not necessarily technology, but it's still going with kind of legacy systems.
Okay, thank you. So let's get into some of the AI questions then that are appearing here on Slido. I don't know who this one's from, but it says, how does AI get checked to ensure that what it considers to be normal agrees with what an experienced engineer would consider to be normal?
Yeah, that's a very good question. Thank you for that. With this system, there becomes a period of learning, which could be several hundred hours. And as we've said before, that engine experts know what is expected. It may well be slightly out of, as I said, every engine is unique. But once the system learns what a particular engine behaves like, then it can see what is abnormal behavior, but it also looks at the traditional mathematical model rules and thresholds to kind of sense check what it's doing. before going to the expert and saying this might be worth looking at. So I think on one of the slides you'd have seen a heat map with the fuel dilution of lube oil. So it clearly, it's flagging up stuff that it's absolutely certain is not right. But it could be several hundred hours before you get to that point. So there is a period of learning before it knows exactly what the behaviour of the engine should be.
Okay, and sort of following up from that, a question from IFA from CBotXR. How does the AI element differ from continuous monitoring and algorithm-based analysis of a data stream? We've lost sound, Karl. You seem to be muted.
Yeah, sorry. So how does it differ to continuous monitoring? I mean,
yeah, and an algorithm-based analysis.
Yeah, that's quite a difficult question to answer, because obviously the algorithms are written specifically for analyzing the data. I guess it's a bit like, well, my kind of understanding of this, it's a bit like computer systems being able to rapidly look at a mass quantity of data based on a particular algorithm, as opposed to just looking at trending data, which can be rule-based. So it's a bit like a search engine, I would guess. I don't know the ins and outs of it. I mean, I could probably get a more clearer answer. And again, it's very difficult to know how much I can actually share with you on the specifics of how the algorithms are written or how they operate. But yeah, that's pretty much all I can really comment on it, to be honest, at my level.
I suppose one of the key differences may be around the learning aspect to it. So it's that continuously learning from the data that's available, and the being able to, as the thing as you explained in your presentation, being able to recognize that all machines are slightly different, and so it's being able to apply that specific knowledge of a particular machine,
Absolutely.
that ability to continuously learn. Just sort of a bit of a follow-up on that from me. Rather than sending all the data ashore, would it be possible to put some of the data analytics, some of this AI at the edge of the system, but on board the platform, that then can be provided maybe with some sort of decision aids that would assist the ship staff to make better decisions, rather than having to transmit the data ashore and become dependent upon the OEM ashore? Would that be a possibility?
I think that's something worth looking into. Given how the Navy operates, and where Naval HQ is, and fleet operations, FOMO, people like that. Obviously that is one kind of route from the OEM into the ship externally. But I guess it's possible to analyze the data locally. The question is the actions needed, beyond that, in terms of the advice to the ship, to the MEO or the maintainer, because what's the data? Well, I think that's probably the crucial point, is that the subject matter expertise is what's needed to make a call and say that this is absolutely worth taking note of, and that's the kind of key part of it. Data is just data without the knowledge. But if you've got that level of knowledge available to you and can advise you. Do you need to do it on board? And clearly you've got trending information from the IPMS, for instance, but actually analysing the data and giving an output locally. I mean, it will show you the data on the laptop, on the service laptop, which they'll have on board. What you do with that data is kind of a critical decision after that, really. So they can see it.
Yeah. Okay. What training requirements would be needed to effectively implement new AI systems?
Again, good question. It's a bit, I would say, minimal, because this is essentially dealing with, smartphones or laptops technology. Because the information is all automatically done in the background, a simple black box and connectivity to the engine, passing information, off the vessel, a one-way transmission of data. It's clearly, how do you operate the software, to be honest, as to how you communicate with the expert, and that can be done, through an application directly into a laptop or a phone. In a commercial world, the chief engineer has a telephone, and he'll get an alert to say this is what we've seen. So, there are no real learning. There is no real training requirement. It's it's no more than using an IT system, Windows-based IT system. It's just it's like what do they call it? DM, digital media.
Yeah. Okay. A couple of similar questions here. First of all, from Commodore Rana, saying that he would assume that from now on, AI would effectively be offered as a standard offering from most engine manufacturers as our learning continuity grows. And a question, a similar supporting question from an anonymous subscriber here. Is it not also therefore a bit of a drawback that we're seeing AI only really around diesel engines at the moment, and we really need to see that expand across other equipments to get the real value here? So what are your thoughts on those two aspects?
So in terms of most manufacturers offering AI, I don't know about other OEMs, but absolutely correct. We are offering, when the engines are bought and installed, that the hardware and the software are all part of that scope of supply. So all we have to do after that is work out the connectivity between the vessel and how they want to set it up. So yep, absolutely, it's part of scope of supply today with any engine that you would buy from us. Is it a drawback because it's only diesel engines? Well, we're working with other equipment within our own organization, so exhaust after treatment, for instance. It's not solely used for diesel engines. It could well be used for gas turbines, but Wartsila is not a gas turbine supplier, so where the expertise would come from would have to be the OEM to do that. And maybe they're creating their own platform to do that, I don't know. But absolutely, it should be used in many different equipments and systems on board, absolutely.
Okay, and a question from Mustafa from Virginia Tech. He'd like to know if you're supporting efforts for introducing AI-based reliability on early stage design of ships.
Yeah, definitely. We are, well, with being involved with new build activity myself, it's often the case that the owners, they think about this well ahead of time now, because gone are the days where there were different budget holders within the organisation that say, I just want a new ship, or I want. I'm not worried about what it costs to run the ship. They think from the off, what are the through life costs of the ship, and how can I best get value for money out of the equipment that I'm buying? In other words, I need to know the condition. I need to work with the OEM, because I don't really want to be replacing components before the end of life. I need to get, I've paid a lot of money for this asset and I need to sweat it. So that is a very key to today's commercial and military new build process. Yeah.
Absolutely. Another question here from Commodore Rakesh. So he's asking, is AI able to effectively combine all sorts of data, thermal data, mechanical parameters, vibrations, engine oil condition, to suggest an overall engine health suggestion of what the overall engine health might be at any particular time?
Yeah, I can't answer the question on fluids, because I think that would need some kind of either manual input or maybe different technology to use on the engine. But certainly, I mean, you've seen that they can indicate that there are issues with, for instance, the lube oil, fuel dilution of lube oil, through the monitoring of bearing temperatures within the engine. What I'm not familiar with, and I don't believe we have it, or anybody has it for that matter, is the ability to analyze fluids remotely. You might be able to look at viscosity, pressures and temperatures, but I don't think that is necessarily automatic. I'm not aware of it if it is. But yeah, you have an overall strategy, maintenance strategy, which involves not only the data, but absolutely fuel, lube oil, and cooling water fluid analysis. So once you're in possession of that, then that's quite a small undertaking compared to ripping the engine apart and replacing 12 heads, just because the maintenance, the hours are supposedly up. So the overall health, the condition, the overall health, I think the operator can get a fair assessment themselves, but a more detailed look and maybe a judgment from the OEM again is helpful to maybe you determine which, for instance, which cylinder head you might want to remove, but let's not remove 12 of them. Let's take a look inside. Let's have a look at the crankcase deflections, crankshaft deflections. Let's have a look at the data, the fluid, take one of the pots off. By and large, can we get another 2,000 hours out of this and wait until next year? That's the sort of advice that I think is necessary and required from an OEM.
Okay.
Sure.
From Rob Dorey, do you think manufacturers will start to insist on AI within monitoring in the future in order to maintain any warranty on the equipment?
Well, certainly AI is very beneficial during warranty, and as I've said, we provide it. So during the warranty period, absolutely, yeah. Because I mean, it's quite common for an operator to they experience a defect, and they'll ring up and say send somebody down. And at that point, you don't necessarily know whether you need a superintendent, a technician, a mechanical guy, an electrical guy. But what this technology will do is help us identify the right resources to send down, and then execute warranty matters in an economic way. So one strategy may be to have what we call a swing set, critical spares held on board, and it may be that the advice is to replace a particular item. And then in slower time, rather than sending people on board, slower time would be to land that item, get it shipped back to the workshop, and had a look at by an expert. So we've avoided travel and subsistence costs, and we provided an immediate defect rectification, based on what we see. But most diesel electric ships have a number of gensets, so they've got a reasonable amount of flexibility in the power for the ship to carry on its normal business. So it's working out really, what is right and sensible. But for sure, AI absolutely helps the equipment manufacturer with warranty, and it should help the user, minimize the intervention of the OEM.
Yeah, absolutely. In your talk, you mentioned dynamic maintenance and the way in which you can exploit AI to pinpoint exactly when maintenance perhaps should be undertaken. Does this lead us to a more of a continuous maintenance regime rather than doing maintenance in fixed planned periods? And do you have any evidence yet to suggest whether AI leads you to a more continuous maintenance regime rather than a planned maintenance regime, or not?
I think it can do. I think it could be a very good thing, because if you were to deploy, for instance, to the Gulf, and the ship was to remain on station and not necessarily come back to the UK, then and due to the fact that she's probably got 4 gensets on board, provided the ship's has got the right level of power, she can carry on her business, then there's nothing wrong with and many of our commercial customers do it. They'll say that we want to do maintenance on the hoof, on the trot. So as they might be sailing from Qatar to South Hook or somewhere. There's no reason why we couldn't have a team on there. Slightly more difficult in a military ship in terms of being on the front line, but doing these actions, and that's probably another area where I find distinct differences in how the commercial world do maintenance to how the Navy do it. And that is, they'll dock the ship and it's in there for 7 days, and they'll get absolute balls out for 7 days, and then the ship goes back into service. So, again, I think that sort of approach could work. Not necessarily, going into dry dock, but a significant effort, if you like, if the ship was alongside in Oman, for instance. There's a huge facility in Oman to workshops and field service. You could take a small team of guys, half a dozen guys, be on board for a week, and then and then get off. It all depends on what the ship is doing, I would say. So if he was about to sail from Oman through the Med into Gibraltar on the way home, you could do stuff on the way home. So it may be that certain lifting, heavy lifting, has to be done while the ship's alongside and stable and no motion. But the Navy's not averse to doing that. They've got gas turbine from previous experience. They've got a dog kennel with a gas turbine in it, or they've got a spare diesel. So in years gone by, the Navy were absolutely on top of exactly that. I think they had a gas turbine change team available, would fly out and spend time on board doing the replacement. So yeah, it's absolutely doable. Actually, another thing that springs to mind is that you know, medium speed engines, they shouldn't need to come out the ship. Everything should be doable within the vessel. So as you know, when you've got a military vessel with not necessarily high hours, because the annual operating hours may not be that great. If you sit down and look at the procedures that have to be done over a period of time, then you can carefully manage that really well.
Okay, thank you, Karl. We're out of time, so we'll need to draw things to a close. Thank you very much, Karl. Thank you also to all our contributors to the discussion. Details of our next webinar will be published shortly, but I would like to take this opportunity just to remind you of a couple of upcoming events. Firstly, the IMarEST annual conference will be taking place online from the 28th of June to the 2nd of July. It's free to all IMarEST members and registration is open, and there will be a naval engineering CEng contribution to that conference. And also the 9th Engine as a Weapon International Symposium and the Marine Electrical and Control Systems Safety Conference will be running concurrently, again online, from the 15th to the 17th of November this year. So please put the dates in your diary, and there's still time to submit an abstract. Thank you again, Karl, and thank you to everyone for joining us, and I hope to see you all again soon. Bye for now.
Thanks, Matt. Bye for now.
Okay, and thank you everyone so much for watching with us today, and of course to our wonderful speaker and host. Just before we close off, I'd like to remind everybody watching online, as you would have seen in your registration details, that we have a virtual networking room. So this is an optional informal platform, but if you'd like to try and connect with other people who are watching today, then you can connect via imarest.org/meet now with the event password webinar. And with that, we will sign off today and hope to see you on IMarEST TV again.